So today I'm going to present ZFS improvement for high-performance computing. So as most of you may know already, based on Gabriel's talk, ZFS backend file system is fully supported in Lustre since Lustre 2.4.0. We actually developed ZFS support as part of a project called Orion, which was funded by Lawrence Livermore. The goal of this project was first to make the high layer of the Lustre stack totally independent of the backing file system, because it was not the case previously. Prior to 2.3, we still had layers that were very tied to some ext4 internals. And secondly, the project was about developing a new object storage device module which can directly talk to the ZFS file system. In our case, we are integrated with the data management unit, DMU, which is a ZFS module. So this project completed in 2011, landed in 2.4.0, but since then we continue to improve ZFS support into Lustre. So for instance, in 2.6.0 we added LFSTK support, and in 2.7 there will be some performance improvement for both data and metadata. So here is what the ZFS IO stack looks like. As you can see, it's very modular. So in the middle here you have the data management unit, which is transactional object store interface, which is built on top of the SPA layer, which is composed of 3 different modules. The SPA layer exports a flat address space with transactional semantic, and it is in charge of managing the memory, the caching, as well as virtual devices. So the virtual devices management involves RedZ, WebZ2 management, checksumming, and mirroring as well. So on top of this object interface provided by DMU, there is a module called ZAP, which stands for ZFS Attribute Processor, which creates key value store on top of DMU object. Then there is another module called ZFS Intent Log, ZIL, which provides the capability to commit to disk some I/O related to a file very quickly, bypassing most of the copy on write semantics, the transactional engine provided by ZFS. At the top layer, you have the ZPL, the ZFS POSIX layer, which creates a file system on top of a DMU object. So it uses ZIL in order to commit some changes quickly to disk, typically in the case of fthink, but also it uses ZAP to represent directory entry and DMU object directly to store data, for instance. Lustre, and more particularly the ZFS OSD, as I mentioned earlier, directly interface with the ZAP and DMU to store Lustre feed on disk in a compatible manner with the ZPL. So it means that the Lustre target can be mounted as a ZPL file system on Linux, because the on-disk layout is totally compatible with between Lustre and ZPL. There is another layer which is probably not so famous, is the ZFS emulated volume, which provides the ability to export volume, so typically through a block device interface or a character device interface to a user space. Then a block device, for instance, can be exported through the network through iSCSI. So I'm not going to provide more details about each layer and how Lustre uses those layers and how we can improve the layer interaction. So first of all, the data management unit, as I said, is a general purpose transactional object store. So an object is represented on disk by a dnode, and a collection of dnode is represent an OBJ set. An OBJ set is also commonly called a data set. The data set is the unit for snapshotting and cloning, and there is transactional semantic on top of those objects. So as I said earlier, it's built on top of the SPA layer, which provides a flight address space. So Lustre and DMU, so Lustre uses a single data set inside the DMU. So it means that all Lustre feeds are created inside the default data set created inside the Z pool. The on-disk format is compatible with ZPL, as I said earlier. There is just one flag that has to be set manually. This is a ZFS set can mount equals yes to make sure that the ZFS does not automatically mount a Lustre target as a ZFS file system. For each OBJ, for each dataset, you have block accounting for each user and group, which is managed by DMU itself. But we also needed dnode accounting for inode quota in Lustre. So there was no accounting available directly in ZFS. So as part of the Reims project, we developed dnode accounting inside the ZFS OSD itself. Unfortunately, we ran into many races and issues, and we finally decided to add directly dnode accounting support inside ZFS itself, inside DMU more particularly. So we provided the patch to the community, to the OpenZFS community, and the patch is being reviewed. Hopefully it will be landed at some time in the future. Also, we did this same kind of improvement with LDiskFS. So we use system attribute with ZFS to make sure that the Lustre XATTR are close to the dnode and even stored inside the dnode. We did the similar type of changes to store XATTR inside the inode with LDiskFS a long time ago. The ZFS attribute processor, so it provides, as I said, a generic key value store association within a DMU object. So there are two types of ZAP: micro ZAP, which intends at handling small key and small values, and fat ZAP, which are large number of entries and long key values. So those ZAP are used by the ZFS POSIX layer to store directory entries, as well as ZFS attribute, but also the hard limit for each user is stored by ZPL inside a dedicated ZAP, and DMU also uses dedicated ZAP to store block accounting for each user in group. So this uses this ZAP layer. Lustre uses ZAP to store all index files on disk. So this includes the directory entry, which is stored in a compatible manner with ZPL, but also, for instance, all the quota files. So the quota index file on the master are stored in dedicated ZAP on the quota master, which is the MDT0 currently, and also on the slaves. So we store on the slave how much space was allocated from the master. So each slave recalls how much space was allocated for each UID, GID, and we store it on disk on the slave through a ZAP. And more importantly, the object index. So we actually have multiple object indexes. I think the default is 64 object indexes on disk. And the goal of the object index is to store the association between the Lustre feed and the dnode ID. Having very fast object index operation is very important for metadata operation. So fast OI insert, lookup, delete is definitely a must-have. So we spent some time analyzing the hash function provided by the ZAP to make sure that all entries inside the OI were uniformly allocated across all the hash bucket, and it turned out that the ZAP is doing a pretty good job at spreading all those entries into hash bucket uniformly. We also realized that ZPL is using a larger indirect and leaf block size that we are using currently in the ZFS OSD. So ZPL is using 16K, while we are using 4K. So we made a patch to change the default inside the ZFS OSD, and this definitely improved the performance with MDS survey for create and destroy by more than 10% actually. And we are considering whether we should go beyond 16K, so we're doing more performance measurement to know whether there is any benefit to increase the size of the leaves. The ZFS intent log, so copy on write is very efficient for long-running transaction, but is not so efficient for very small transaction. The problem is that in order to update just one block inside in a leaf, you have then to copy and write all parent block up to the root of the tree, which is the upper block in ZFS. So if you have many blocks to update, many leaves to update then the cost is the metadata overhead is negligible. But obviously, if you update just one leaf, then the copy on write cost is pretty high due to the metadata overhead. So to work around this, ZFS has a module which is called the ZIL here, the ZFS intent log. We just provide a quick journal on this, so it can be either stored in the main Z pool or in the dedicated device, which is a log device. We can be on SSD or spinning disk. And this provides the capability to ZFS, to ZPL, to quickly flush I/O operation related to a given file. The changes will still be committed as part of the regular transaction group commit with the copy and write semantic. So most of the time, the ZIL will be discarded. So we have fthink that's write into the ZIL. Then transaction commit that happens, it will write the data at the right place inside the Z pool. So most of the time, the ZIL is just discarded. Just in the case where you hit a problem, a failure, the node restarts, for instance, and the transaction group did not make it to the disk. Then in this case, ZFS will parse this special log journal and re-execute, replay all I/O operations that were logged into this special log. So as I said, it can be stored in a dedicated device, and there is a limit of 64K. So all I/O operations that are smaller than 64K will be written into the ZIL device, and then will commit and will be written again and reapplied again when it lands to the main Z pool. However, if the I/O size is bigger than 64K, the data will be written directly into the Z pool, and we will log ZFS will log a record inside the ZIL. Then at transaction commit time, we are not going to have to rewrite the data inside the Z pool. The ZIL will just play with the metadata pointer to point at the data that is already written to disk as part of the ZIL flush. So unfortunately, Lustre does not take advantage of the ZIL yet because it requires changes inside the ZFS OSD to interface with the ZIL module. So it means that for the time being, synchronous I/O operations are pretty impactful on top of Lustre with ZFS backend, so typically ODirect, or ODSync, or fthink. And there are also some internal Lustre mechanisms that may trigger fthink on top of the backend file system. So commit on share is one of them, and there is also sync on log cancel. So we are considering in LU 4009 supporting the ZIL, and we are making changes to the code in order to support that. One of the main problems, which is fixable in our opinion, is that ZIL replay may break the Lustre transaction number ordering. So if you have changes to file A that got assigned the transaction number N, and then changes to file B that got assigned transaction number N plus 1. If someone call fthink on file B, we will write all changes associated with transaction N plus 1 to the ZIL record. Then if you crash at that point and you restart, none of the I/O from file B that were assigned to transaction N have been landed to disk because the transaction has not committed, but the ZPL are going to replay I/Os for transaction N plus 1 and apply them to disk. So the end result that we will see I/O for transaction N plus 1, but not the one for transaction N. And the Lustre protocol usually rely on the fact that if transaction N plus 1 is committed, it means that all prior transactions were committed as well to disk. So there are solutions to this that are being discussed in LU 4009 if you are interested. So the adaptive replacement cache is the central point of memory management for ZFS. So this is the replacement for the Linux page cache. So in the future, ZFS on Linux might consider being better integrated with the page cache, but currently it's a separate module which manages memory by itself. It is a self-tuning cache adjusted based on I/O workload, and it even has its own I/O scheduler to disk. So one problem, we realized that Lustre OI entry are typically treated as data by ZFS. So inside the ARC, we have Lustre metadata as well as Lustre data. And it's quite important to keep active OI entry inside the ARC cache to make sure that each time we do a lookup, we don't have to go to disk in order to look up the dnode we have actually to access for the given feed. So we did some work in this area, and the first patch, which I think is landed, is the LU cache interaction. So we have our own LU cache inside Lustre for the LU stack, and this cache was growing again and again, putting more pressure on the ARC and causing entry for the OI to be evicted, which impacted performance. So we did some change in LU 5164 to limit the size of the LU cache and to give a chance to the ARC cache to cache OI entry efficiently. Another aspect of this work is the feed prefetching. So there is some function that can be called through the ARC in order at the beginning of the request processing, where we can tell the ARC we are going to need this entry, this entry, this entry. So please prefetch them whenever you can afford. So this is being done under LU 5049. So ZFS supports variable block size. We can go up to 128K, but unfortunately 128K is sometimes not enough for HPC workload. And there are still cases where 1 megabyte block size, and even bigger than that, 4 megabytes, 16 megabytes, will benefit and will be interesting to support. So one example is when you have a RAID array that is optimized for 1 megabyte I/O, and ZFS sends 128K I/O. If you are in write-through mode, so this is a real-life issue that I had with some DDN storage configuring write-through mode. So we work out with IRA that actually for every I/O done by ZFS, which was 128K, we were doing a read modified write over 1 megabyte on the controller. So it was definitely impacting performance significantly. Obviously, enabling write-back cache help with this particular problem, but doing 1 megabyte I/O, and more importantly, if they can be aligned on the backend device, because those storage controllers are also very sensitive to I/O alignment, we will definitely get better performance. Another example is copy on write. With copy on write, we basically always write sequentially, regardless of the ordering of the I/O. When you do a transaction commit, but the problem is that when you read with a different pattern, then you end up doing random block read from disk due to the copy on write aspect of ZFS. And definitely having a larger block size of 1 megabyte would help because we will do better with 1 megabyte random read than with 128K random reads. There is, also it will help a lot with severing and scrubbing time. So we have a draft patch available on the GitHub from ZFS on Linux to support 1 megabyte block size and even beyond. So it's currently available for testing, and we are testing it. ZFS on Linux comes with DKMS support. It means that you don't have to rebuild the ZFS module by yourself. It's done automatically through RPM installation. So it will pick up your kernel, rebuild automatically against your kernel, and install the module. We did the exact same work with Lustre server-side RPMs, which are with no support DKMS. So it means that you install the Lustre server RPM, and it will automatically rebuild against the kernel and get the ZFS version available and installed on your on the server. And for further upgrade, if you upgrade ZFS of the kernel, the Lustre module will be recompiled automatically. So there was a future announcement that we are also considering. So multiple mount protection was available in LDiskFS for a while. So it prevents a target from being mounted multiple times on different OSS. We have some design to implement the same kind of functionality inside ZFS. Large dnode support. The larger the dnode, the more extended attributes we will be able to store close to or inside the dnode, or close to the dnode metadata, and the less sick we will have, so better performance will be expected with large in-ARC support. So L2 ARC is yet another level of caching beyond the ARC. It can use SSD in order to do caching between memory and the Z pool. Currently, it's not resilient. It means that if you reboot, you lose all data that are stored inside your L2 arc. And the L2 arc will have to be repopulated after each reboot. So this is another issue which we might want to fix. And finally, there are some RAID-Z and RAID-Z 2 improvements that, like parity declustering, that can be considered in the future to improve resilvering. So as part of the Fast Forward project, which completed in June of this year, we developed a modified version of the ZFS OSD, which was able to take advantage of multiple datasets inside the ZFS, inside DMU. So the way it works is that we created a new entity, which is called a shard, which mapped directly into a ZFS dataset. Then several shards across multiple targets were gathered into a new concept called a container. The container was the high-level object for which we were triggering a regular snapshot. So a snapshot at the container level resulted in snapshot done at each individual OBJ set on each target, which allow us to have a consistent view of the container across multiple targets. Another feature we wanted to use in addition to snapshotting inside ZFS is we wanted to be able to accept I/O for any version at any time. So the container had version 1, for instance, and we wanted to be able to log I/O for version 2, version 3, version 10, version 1000 at any time and have no window to accept I/O for future version. So to do so, we implemented a modified version of the ZIL. Unfortunately, the ZIL was not exactly what we needed because the ZIL is still very tied to the transaction commit. You have one ZIL in flight for all changes that will be discarded the next time the TXG flushes. But in this case, we wanted to be able to integrate changes really on demand, not on the next TXG flush, but just when the application requested for a special version to be integrated. So we modified the ZIL and come up with a new intent log called the version intent log, which was able to log I/O operation and integrate them on demand later. So the work done as part of the Fast Forward is definitely not directly useful, at least the ZFS changes to Lustre, but definitely it helped us to play with a snapshot and the ZIL and have better understanding of how those mechanisms interact and might benefit POSIX cluster in the near term. I think that's all I have for today.
Do we have any questions?
Is there any question?
The question is not so much.
I don't know how to blink the light. the light.
Actually, the question is not really related so much to Lustre, but can you comment on that? When or will it ever happen that ZFS will be part of the official Linux kernel? Or what stops it?
The problem is the licensing, right? The CDDL license and GPL are not compatible, so it's not possible for ZFS to be shipped at the same time as the Linux kernel.
And are there any plans to develop new branches? Do you know from any development in this direction, or so?
Well, there is definitely ZFS on Linux. The Git repository is available, and even without any kernel understanding, you can install easily ZFS on Linux through the DKMS capability that I mentioned. It will fetch automatically the RPM, install them, and compile them. But definitely, in the foreseeable future, ZFS won't be integrated in the kernel unless Oracle decides to release it under a GPL license.
And how is the community work between the different ZFS forks? So there was when Sun was bought by Oracle, it was closed. I think it was this version 5000.
Yeah.
And there was encryption, but all these forks does not have encryption. Also not the ZFS.
So actually, there is the Open ZFS community, which has the ZFS version on Illuminos, which is the old version of Open, or the old Open Solaris. There is also on BSD, so ZFS is supported on BSD and also on Linux. So there is a community around that make compatible changes and have the same code base. And then there is the Solaris proprietary ZFS, which moved on independently of the OpenZFS community. But at least all the open source effort is done all together, and people are working together to make sure that the same features are available across all the open source platform.
Okay, thank you.